Here's our first sample problem for KSP. So what is the value of KSP for tin 2-sulfide given that its solubility is 5.2 times 10 to the minus 12 grams per 100 grams of water? Now this is a very common way of, this here is a common way of expressing the solubility of a compound, the grams of the compound that will dissolve in 100 grams of water. But we don't really want that. We want what's called a molar solubility. Which will be basically the concentration of ions for a saturated solution. So if I want that, I'm going to use a slight trick here, right? So my reaction is that I've got tin 2-sulfide, which is going to dissociate into its ions. And I could find the concentration of one of the solutions, but really what this is saying is that this many grams of tin 2-sulfide is soluble. So I'm going to do a little trick here where I turn that into a concentration, where I say I want to know the moles of tin 2-sulfide that will dissolve in a liter of solution. All right, so I'm going to do 5.2 times 10 to the minus 12 grams of tin 2-sulfide over 100 grams of water. All right, I'm going to use molar mass to get the moles of tin 2-sulfide. And then I'm going to use the density of water and then convert the milliliters to liters. So when I do that, I get a value of 3.44885 times 10 to the minus 13 moles tin 2-sulfide per liter solution. Okay, now this is slightly a lie, okay, because the tin 2-sulfide, if we put that in solution, it breaks apart into its ions. So it's not actually tin 2-sulfide anymore, it's ions. But we can use that as a handy starting point, okay? Now, the next thing that we're going to do is we're going to use what's called a Rice table. So Rice stands for reaction, initial conditions, the change, and then the equilibrium conditions. And these are done in moles per liter or molar, depending on whether you have a gas or, in this case, you have aqueous stuff. Okay, so my reaction I put in, all right, my initial concentration of the tin 2-sulfide for a concentrated solution is this concentration. So I'm going to abbreviate it as 3.4 times 10 to the minus 13 molar. Okay, and if this is going to be a saturated solution, all of that solid that I put in is going to break apart into its ions. So its equilibrium concentration is going to be 0. All right, there are also probably some other things that we could give numbers to, which is our initial concentration of our products. So before the reaction runs, our initial concentration of products are 0. We don't have any products before the reaction is run. Okay, so let's start thinking about change. So this one will go down by 3.4 times 10 to the minus 13 molar because it starts with 3.4 times 10 to the minus 13 molar and it ends at 0 molar. And since both of my products are in a 1-to-1 ratio, I can do, this one's going to go up by 3.4 times 10 to the minus 13 molar. And this one is also going to go up by 3.4 times 10 to the minus 13 molar. And so my equilibrium concentrations of each of these is 3.4 times 10 to the minus 13 molar. And now I can do my my equilibrium expression, KSP equals concentration of SN2 plus times the concentration of S2 minus. Okay, and keep in mind that these values for concentration, these are the values at equilibrium. So it's the nice thing about using a race table is if you have these equilibrium values, you know exactly what to plug in your equilibrium expression. So since both of these have the same concentration, I can just say that the equilibrium solubility product is just going to be 3.4 times 10 to the minus 13 times 3.4 times 10 to the minus 13, which I'm going to express as 3.44885 times 10 to the minus 13 molar squared. Okay, and then when I do that, I get 1.2 times 10 to the minus 25. And that is my KSP value. And notice that this is only 2 sig figs. Okay, so these are kind of the longest version of these ones where you're given this solubility in grams per 100 grams. It's a little easier. You can skip this step if you're given a molar solubility, but you still do a Rice table and then your equilibrium expression to solve.